Mhm. Okay, so, and we are trying different connections here. We try different connections. So this is a protocol independent, and in case there are multiple IP addresses used by a specific service domain. This is a data structure that looks like this. So this is P, and what it points to is a list of address info structs. Now the important ones are these socket. This is a socket address structure. This contains the IP address and the port of a specific host, and you have many of these. Like I was saying, large-scale services have different use different IP addresses to serve, many different clients. So what you need to specify is the host name, and then it will return you this list, and you can try each of the IP addresses, connecting to each of the IP addresses, and whatever succeeds, you take that. So they limit the specific IP addresses that can connect to based on regions and all that. Right? So this is a generic way to connect to a specific service. And then there's a lot of other flags here that are set automatically when you call this function. So if you look here, we are not providing the arguments of the socket system call ourselves. We are using the whatever is inside P, the list returned by this function, and we are using the address, family, and socket type returned by the get address info function. So we're not taking any guesses what this is and what this is. Even though for our purposes, these will be AF INET and SOC stream. So if you see in this for loop, we are trying to connect to, using our file descriptor, each of these. So P address, this is the socket address structure that we are really interested in. And we are not creating it ourselves. We are just using it, what is returned by the get address info function. So similarly, on the server side, there's an open listen FT. So you don't have to create a socket yourself. You don't have to create, you don't have to call bind yourself. You can just get a socket from a listening socket from open listen FT. So here they get a socket. This is something they do for errors, and they bind it, and then they close it. So listen is called outside of this function. Okay, so let's, okay, no, sorry. Listen is called after, and it's on the next slide. So then you call listen. Okay, so you just need to specify in your applications, you don't even have to worry about socket, bind, listen. You just use this one function and it will return you a listening socket. It's as simple as it gets. And you just need to provide the port number. And use this function. If you understand what's happening inside the function, it's great. Otherwise, you can just use the API as it is. So on the server side, you need to use open listen FT, provide the port. On the client side, you need to provide the host name and the port number. So let's look at a very simple network application called the Echo server. The client, in this application, the client reads a line from standard input. On the client side, someone types in from the keyboard a line. The client sends the line to a server process, and the server echoes back whatever the client sends. So the server receives the line and echoes it or writes it back to the client. So this is a simple echo server that we want to build today. Let me now open a shell. And let's do some work in the shell. I'm going to stop sharing. I want to share the terminal. See at the top. So here's my all the binaries that I want. Okay, good. You can see it. So I have a Echo client and Echo server. Okay, I have two binaries, two programs. One is Echo client, one is Echo server, and they are saved in my directory. Let me fire up the server first. So if I run, so you will be running this, you will be modifying this in next week labs. If I just run the binary, it tells me, hey, what port number do you want to start the service at? Now I cannot use 80. Okay, 80 is a well-known port used by web servers. Whenever you have requests, whenever you request a web page from a server, this port is already taken. Let me try 25. Okay. 25 doesn't work because I want to start a new server. I'm starting a new service in the world. So I need to pick a new port. These ports are all taken. Okay, so let me just take, let me take a wild guess. Works, okay? The server is now running. So first I want to show you what this does. Then we will look at the code. So the server starts running. Now, I don't want to open a second shell terminal and start the client, because then over Zoom, people will not see it. So what can I do? I can run the server in the background using ampersand, right? We did that a while ago. If I use ampersand here, the server will run in the background, okay? Now the server is running in the background and the terminal is free for me to do something else, okay? So this is one way you can do it. Or you can open a second terminal. Echo server is one process with its private virtual address space. And the client is a separate process with its own virtual address space. You can run them on separate terminals, or you can run them in the same terminal. If I want to do other work, if I want to start a client here, I can just send the server to the background like I did. So now the client wants to connect to the server. I've started a server on port 8000. And the way the Echo server is written, we will soon look at the code. It's telling the server is telling the kernel, whatever IP address the client uses, I don't care. Just send me the message. The port is important, but I don't care. Whatever IP address the client uses, just send me the message. Okay, so I'm just going to use 0 here, 0, 0, 0, 0. And I'm going to use but the port number is important. The port number is important. The server is listening on a special port 8000. I just started the server. So I'm going to start the client, and we will look at the code in a bit, but you can trust me, trust my word that what connected to localhost port number, this line has been printed by the server. The connection has succeeded, okay? Now, the client didn't pick the port and the IP address because it's not that important. The kernel just picked whatever IP address was available. Each host on Linux has a special Unix domain, and that domain has a special address, localhost, domain name, sorry, localhost. And the kernel just picked a random port for the client, 41730, but the server has the identity of whoever connected to it. So this is the server printing, okay, I'm connected to localhost 41730. So this connection between the server and the client has now established. So in the labs, you have to do this. You have to fire up the server. You can do it like I did here in one terminal, or you can have two terminals. In one, start the server, in the other one, start the client, and then go back to the terminal where you started the server and check if there's a message connected to blah. So now I'm going to write so we are on a spaceship and we are having a conversation. So I say enter. The server says received 37 bytes, and it sends back whatever we say to the server. Hello, we are comp 2010. Who are you? Okay, so if I say server says, it's pretty dumb. It will keep echoing back what I say. So I want to get inside the code now to see how this is happening. Okay. Now I did Control C. Control C killed the client, but it did not kill the server. The server is running in the background. And if I look at the list of all the processes, I can see that the server is still running. The first one here, Echo Server I 8000 is still running. When you run processes in the background using ampersand, you need to do something special then to kill them. So this is a drawback of using one terminal. Now you have to kill it manually. There's an application, Telnet on Linux, that does the same what our client application is doing. So if I do trying the IP address localhost, connected to localhost, and then the server is saying connected to localhost this. So and so the server, so this also works. So whatever the code we have written in Echo Client that I'm going to show you, you can also use Telnet for these kind of things. And Telnet is a very useful application that we will use from time to time in the coming labs. So here's the client code. Very few lines of code. So let's see what the client is doing. So we are reading host and port from the command line, lines 17 and 18. The client is getting an appropriate file descriptor from using Open Client FT. Like I said, if you understand what's happening inside Open Client FT, it's great. It will help you debug your applications, but you don't really need to understand beyond that. You can just use the API. Open Client FT, host and port. And then we are using the RIO, robust IO package to do the communication. So on line number 23, we are using fgets to read a line from standard input. There are 3 arguments on line 23. We are providing fgets with a buffer. We are providing the maximum length of the line that we can read. And we are providing a file descriptor. Sorry, it's not a file descriptor. It's a file stream, std_in. std_in, std_out, std_error are file streams that are associated with every process by default. So we use fgets to read a line on the client side from the keyboard, from standard input. And if it is not null, what we are doing is we are using the write n function to write on that file descriptor, client FT. So on the client FT file descriptor, we are writing whatever is inside the buff, right? So I've been telling you to learn to use these functions in the previous labs, and that's the reason. Now, this client FT could have been a different file descriptor. It could have been a file descriptor for a file on disk. It doesn't matter. RIO write n doesn't care. All it cares is that the first argument is a file descriptor. Doesn't matter if you're writing to a network, doesn't matter if you're writing to disk, doesn't matter if you're writing to a solid state drive, to a CD-ROM, as long as you give it a file descriptor, it will do its work. And that's why file is a powerful abstraction in Unix. Once you have a file descriptor, you can use the functions you wrote for storage IO now to do network IO. Okay, as long as the file descriptor abstracts the resource, whether it is storage, disk, network, getting the appropriate file descriptor on line 20 is the important thing. And on line 20, we are providing Open Client FT with the host name and the port number. So the client file descriptor that is returned by Open Client FT is associated with a specific host and a specific port. Okay. So client FT is an endpoint on the client side for communicating with a server that has a host and port as its identity. So we read something from standard input on line 23, line 25, line 23, line 24, we write it. Write means sending a message. So when you're writing on a file descriptor, it's going through the kernel, TCP/IP stack, through the network card, to the host and the port on the other endpoint. That is the server. Now the client calls read line, because we know that the way we have written the server is going to echo the line back, right? The server is going to send us what we are sending the server. So on line 25, we are anticipating that the server is going to send us what we just sent the server. Okay, so we call read line because we want to receive something. All right, I write something on the keyboard. That happens on line 23. The client sends it to the server, and the server is now sending it back. So I call read line B on line 25. On line 26, I display it on the screen. fputs takes a buffer. The second argument is a file stream stdout. So whatever it receives from the server, which is exactly what we just sent to the server, it displays it on the screen. Standard input, standard output. This function, so now we were building up processes, storage IO, everything will come together in the networking part of the course. So you need to recall all these things. Okay, so this is the client that reads something from the keyboard, sends it to the server echoes it back, the client receives it or /reads it and displays it on the screen using standard input, standard output file streams. So what would be happening on the server side? So here, the server is opening a listen file descriptor on line 22. And in a while one loop, this is a while one loop, the server never ever breaks, right? It keeps on going forever. It's using accept at line 25 to accept a connection from the client, okay? So on line 24, it's providing its argument, the listen file descriptor that it has, a data structure to get the identity of the client that calls the server, and then some things that you can look at yourself. Get name info takes the client's identity in this data structure and gives you in English the port number and the IP address. Line 27 is what I told you, that this message connected to blah blah is coming from the server. So you can see that on line 27. On line 28, the server calls a function echo, and it gives that function, provides that function with the argument connected file descriptor. And the connected file descriptor is returned at line 24 when the server calls accept. So the server blocks in accept on line 24 when the client makes a connection, a connected file descriptor is returned for this specific conversation. And then the function calls echo. So what's echo? What's happening inside echo? So on the left side is echo. What's happening in echo? So you create a buffer of size max line. You initialize the RIO data structure on line 13. And on line 14, you are reading whatever the client is sending you. And this read line function takes the RIO structure as an argument, and the RIO structure encapsulate the connected file descriptor that we give to this function echo. And then what is the echo function doing? It's reading something in buffer, which is the second argument, and it's writing that buffer on that connected file descriptor. So it's reading something and writing it back. Right? You take what you give me. So this is the echo function. Using the RIO write and function. Okay, so if you notice, the server is not reading anything. It's doing all that work in the echo function. In the echo function on the left, the server is reading, as in receiving something, and then sending something. And that what the server is sending is exactly what the client sends. I might want to show you. So okay, these are the functions that we've been seeing on the slides. There is a function that does the main work, most of the work, and that is with small letters. And then there is an encapsulation of that with capital letters and where they handle the error. So if we look at the read line function, you don't really have to, I've been telling you to try and understand what's inside these functions. But the key is to be able to use these functions properly. What parameters, what are the input arguments of these functions? Because you will need to use these functions in the applications that you're going to write now. So you need to know how to use these functions. Now, knowing what the function is doing helps if you eyeball the code. So here we are one character at a time reading something. So this is a read line function at the top right. And so in a for loop, we are reading one character at a time, and RIO read function reads one character in the character C here. It stores it in the buffer, and when there is a new line, it breaks, and then it returns the length of the, so pretty simple, right? So this function, if you can just look at the code quickly, it's great. It will help with your understanding. But the key here is that you have to know what each of these functions is doing. There are 3 or 4 of them. And you have to use these functions in the applications that you're going to write now, just like the Echo client server applications. So Echo client and Echo server, the key is how to open a file descriptor that abstracts the network card, the IP address, and the port. Everything else is what we did in the previous labs. Reading and writing, nothing. There's no difference between treating the file descriptor as representing a disk or a network. Okay. So let's go back to our slides and see how much time we have. So what we have done so far is how to establish connections between two processes and how to enable communication between the two processes. So we are going to study, we are going to end this part of the networking part of the course by looking at how to build a simple web server. This web server will serve simple HTTP requests, and HTTP is a protocol that web servers use. So clients and servers communicate using this hypertext transfer protocol. This is an application level protocol. So TCP/IP is implemented inside the kernel. It is not exposed to the user except the sockets through the sockets API. You have to use the API and everything happens inside the kernel. The HTTP protocol is an application level protocol. Applications can send requests and receive messages that follow a specific format. So first of all, clients and server establish TCP connection. We know this by now. Using Open Client FT, Open Listen FT, clients and server establish connection. Clients request content and servers respond with the requested content. In web services, typically servers, a server returns information to the client or a web browser. It tells the web browser how to generate a specific web page. So this is where HTTP is different from TCP/IP. It's a bunch of rules telling clients how to generate a web page. It doesn't actually returns web page as a file that the client can just display. It returns formatting information, tags, rules. Here's how you can generate the web page. This is what it returns. So for instance, one line could be, display. So the server will return something like this, and the client knows that it needs to display COM2310 as boldface. So this is how the HTTP protocol works. So web servers return content to clients, and the content is a sequence of bytes with an associate MIME type. MIME is a protocol that tells the client, what kind of content is this. So it could be plain text, it could be an image. So it helps the client client here is a web browser in displaying the specific bytes that are returned by the server. So everything else is similar. There are two endpoints. So this is the web browser, this is a server, and on top of the TCP, instead of TCP IP requests, we are sending HTTP request and HTTP response. Okay, and these requests and response messages have a specific format, and we need to client and server both need to follow that format. So the content returned here could be static or dynamic. Static content means content that is stored in files. So HTML files, images, audio clips, and dynamic content is content produced on the fly. For instance, the client could say, execute this program for me and return the result. In all cases, web content is associated with a file that is managed by the server. In the case of dynamic content, the file is an executable that the server is managing. In the case of static content, it's a HTML file or something else. So when the client establishes a connection and requests a file, they use the notion of URL or universal resource locator. An example URL is the domain name, the port. So typically you can drop the port because the web clients can put that automatically. It's known that HTTP requests, web services use the port 80. And the file name that you're looking for. So in this example URL, clients use the prefix to infer the kind of protocol the server is using, the domain name of the server, where the server is, and on what port the server is serving web services or web requests for web pages. And server, after receiving the connection, looks at the remaining part, the suffix, to figure out what kind of content is this client looking for. And this tells the server if the request is for a static content or dynamic content. We will see that whenever clients request dynamic content, there is CGI bin somewhere in the path of the URL. And that helps the server decide if the request is for a static content or dynamic content. So this slash here, is not the root directory, the way we use the notion of root directory in the Linux file system. This is the home directory on the server side. So the server expands it to pre-configured default home.html or index.html. Different servers use different, typically it's index.html. So if you don't put this, the server will infer it as looking for index.html. So the client really needs to know all this. This part here is used to establish a connection, and this part is used by the server to figure out what exactly is this client or this web browser looking for. And this URL, if you type it in your web browser, will take you to cmu.edu port number 80, and the server there will know that you are looking for the home page, which is index.html. and that this request is for static content. So a HTTP request is a request line followed by 0 or more headers. So this is this communication, the HTTP protocol, this communication takes place using specific request messages and response messages, and those messages have a specific format. So on the request side, the format is method URI version. Method could be get, post, options, head, put. We are only concerned with get, because otherwise things will get too complicated. So in the labs, we are not going to ask you to implement get, post, options, head, put, delete, trace. Get means give me something, get a page. Okay. URI is typically URL for proxies and URL suffix for servers. Proxies are strategically located between the client and the server to enable long distance communication very fast. So proxies intercept client requests if they are regionally closer to the client, so the client doesn't have to wait for response from far away. So we will study proxies in detail next week. So the second one is URI, which is similar to URL. So it's URL suffix for servers. So this would be slash or slash index.html. Method would be get. So this is one request. And version could be HTTP 1.1. So this is one example of a request. Okay. And then there are request headers that convey more information about the HTTP request. So header name, header data, and one example is host www.cmu.edu. Okay, so here's an example. Okay. Okay, so together the header and the request is telling everything to the server. Get the home page. We are using this version of the protocol, and the server is in the header, host, and the domain name. Okay, the responses have, each response line also has one or more headers followed by content that the client is looking for. So response lines look like, version number, status code, status message, and status code could be 200, 301, 404, and the message could be not found, and that you might have received this not found and all that. So these are responses returned by the server based on the client requests. And the request header provides additional information about the response, content type, content length, and then the content itself. And the content typically is HTML program that tells the client how to generate the web page, how to transform the HTML code into a web page. So here's an example transaction. So we're using Telnet to connect to this domain and this port. Telnet tells you how to terminate the connection, caret and this bracket. And this is on Mac, at least, this is Control-C. So we are saying get the home page, the root directory here, / HTTP version, and then we are using a header, host www.cmu.edu, and we are pressing enter to end the request. And then the host, the server is responding with the response the page move permanently, date, server, location, blah, 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 all this, okay? So in HTTP, \r/n terminates the request. This is line feed, and this is carriage return. And the historical reason for that, I discussed it last week, is it comes from the days of the typewriter, where carriage return means going to the start of the line, and line feed means going to the next line. This is how typewriters used to work. And if we try again, whatever the response is telling us, the transaction succeeds. Okay, so I wanted to talk about the Tiny Web Server today and the networking side of the course, but I think I'll have to talk about Tiny Web Server next week. But there will be Tiny Web Server in the next lab. So the next lab would be looking at the Echo client server code that I just showed you and making a small modification. Instead of echoing the line back, we will ask you to do something else. Send something else, right? And Tiny Web Server is really a web server that it's amazing that 240 lines of code can teach you how to write a web server. If you understand these 240 lines of code, you can write really good network applications. This is already a web server. So I will look at that next week. It's really not that hard. And internally, it's also using RIO write-in, mmap, munmap. The only things that are really new are how to open a file descriptor, how to deal with sockets. After that, everything at printf, RIO, write-in is all that you know from storage IO. And okay, so next week, I will also teach you how to write applications where you request dynamic content, where you tell the server, hey, run a program for me and send me the output. So expect in your lab both the Echo client server and the Tiny Web Server, and we'll see how many labs we need for networking stuff. All right, take care. Mm-hmm.